Hello, welcome to this lesson. In this video, we are going to solve this question I have on the screen. The question says the right circular cone is formed by revolving the shaded area around the x-axis. Determine the moment of inertia and express the result in terms of the total mass m of the cone. The cone has a constant density rho. So let's look at how we are going to solve this question. So you see that I have two figures on the screen, figure A and figure B. Figure A is the actual figure that will be given to you, okay, and then figure B will be the free body diagram that you have to draw. It's the same as the figure A, just that the orientation is different. Okay, so you have to draw your free body diagram this way because of the disc method that we are using, okay, so that you can be able to draw and then portray the disc well. So from the figure that we are given, we have our free body diagram, okay, and then we are using the disc method. So we have a disc drawn in the figure B, okay, which is this disc that we have here, okay. That's the reason I have the disc there, because we are going to use the disc method to solve this question. So we have to determine the moment of inertia and then express the result in terms of the total mass m of the cone. Okay, so let's look at what you are going to do. Okay, so now to solve this question, you are going to use the disc method like I said earlier on. Okay, so you are going to use the disc method to find the total mass moment of inertia of the circular cone. Okay, so what we do is that we will assume that this circular cone is made up of small circular discs. Okay, so the circular discs are piled up to form the circular cone. So what you do is that you find the mass moment of inertia of all these circular discs, okay, and then that will be equal to the mass moment of inertia for the circular cone. So you're going to consider just a single circular disc, okay, and then when you find the mass moment of inertia for that circular disc, we can integrate it to get the mass moment of inertia for the entire circular cone. So let's look at what you are going to do. So since the circular disc just forms part of the circular cone, we are going to consider the mass of this circular disc that are drawn here to be dm. Okay, we're going to consider the mass to be dm, and from the formula density equals mass over volume. Okay, we can say that the mass of the circular cylinder is dm, and then the volume v will be dv. Okay, so from here we can have the density rho to be equal to dm over dv, right? So from here we can see that the mass dm will be equal to rho dv. So this will be the expression for the mass of the circular disc. Okay, so let's look at what you are going to do. So since you are using a circular disc, okay, we will have to consider the volume of the circular disc, which is the dv, and then that will be the same as the volume of a cylinder, which is pi r squared h. Okay, but in this case, the radius of the circular disc is y. Okay, so we say r equals y, and then the height is the thickness, which is the x. So h is equal to the x. So when I write this, I'll get the v to be equal to pi y squared dx. So this will be the expression for the volume. But let's take note of something. You can see that from the question that was given, we have an expression for y, which is this expression. So you can substitute that into the volume expression that we just generated. Okay, so let's look at that. So we have y to be equal to r over h multiplying x, right? So that means y squared will be equal to r squared over h squared. Okay, let me put this in brackets, multiplying x squared, right? So you can substitute this back into this expression. So you're going to have dv to be equal to pi y squared, which is r squared over h squared, okay, multiplying x squared dx. So this will be the new expression for the volume. So now let's rewrite the expression for the mass. We're going to have the m to be equal to rho pi, okay, rho pi, and then I'm going to have r squared over h squared multiplying s squared dx. Okay, so now what we do is that this is just the mass of the smaller or the mass of the small circular disc that we have, but you want to find the entire mass of the circular cone. So what you have to do is to integrate this whole expression. Okay, so you have to integrate this. So when I perform this integral on the left hand side, you're going to have the mass m to be equal to the integral of what you have on the right hand side. But on the right hand side, you see that the only variable we have here will be the x. So which means we can have rho pi multiplying r squared over h squared being placed in front of the integral sign. Then we're going to have x squared dx. Okay, this is what we will have. So now what you do is that you are going to integrate this expression x squared with respect to x. Okay, so you will have to change this indefinite integral to definite integral. But before you can do this, we will need some boundary values so that we can be able to change this indefinite integral to definite integral. And we are integrating this expression with respect to what? X. Okay, so we'll have to go back to the figure that was given to us, and then when you look at this figure, you see that the height of the cone is given to be h, and that is in the x-axis direction. Okay, that's in the x-axis direction. So for this reason, we are going to integrate this expression from 0 to h so that you can get the integration, or so you can get the mass for the entire circular cone. Okay, so this is actually representing the height of the cone. Okay, so let's continue the integration. So we're going to have m equals rho pi. Don't forget we were told that the density is constant. Okay, so we're going to have rho pi r squared over h squared, and then let's do the integration. So for the integration, we're going to have s cubed over 3. Okay, and then you're going to have the boundary to be from 0 to h. So when I do this, we are going to have the mass to be equal to rho pi multiplying r squared over h squared, and then we're going to have h cubed over 3. Okay, so this will be cancelled out, and then at the end we are going to have the mass to be equal to m equals rho pi r squared h over 3. Okay, so this is what we have now. Okay, so now that you have the mass, we can go ahead and then find the moment of inertia of the circular cone and then express it in terms of the mass. So let's go ahead and then do this. Okay, so in finding the mass moment of inertia, what you are going to do is that you are going to find the mass moment of inertia of a single circular disc. Okay, and then when we find the mass moment of inertia of a single circular disc, then we integrate that expression to get the actual mass moment of inertia of the circular cone that we have. So the mass moment of inertia of the circular disc will be equal to half times the mass times the square root of the radius. Okay, this is what you have. But you want to find for a single circular disc, so you are going to have di, and then since we are finding the mass moment of inertia by the x-axis, I'm going to bring a subscript x here. So we're going to have the ix will be equal to half m, and we know the mass of the circular disc to be dm, right? And then the radius to be y, so we're going to have y squared. Okay, so I actually cleaned the expression for the mass, so let me write this again. So we're going to have for the mass we have the m to be equal to rho pi y squared dx. Okay, this is what you have, and then we have an expression for y, so we're going to have the m to be equal to rho pi r squared over h squared multiplying x squared dx, right? So this is what you have. Okay, so now let's do this substitution and see what you are going to get. So we're going to have the ix to be equal to half the m, which is rho pi r squared over h squared multiplying x squared dx, right? And then don't forget we still have y squared here, right? So let's bring it. So times y squared. So that will give us all this multiplying r squared over h squared multiplying x squared, right? So let's simplify this. When I simplify this, let me continue from the top. So when I simplify this, we're going to have the ix to be equal to half rho pi, and then we're going to have r to the power 4 over h to the power 4, okay, multiplying x to the power 4 dx. So this will be the mass moment of inertia for just a single circular disc, but you want the mass moment of inertia for the entire circular cone. So you have to integrate this expression. Okay, so when we integrate this, we're going to have ix to be equal to every other all the variables we have here. Okay, the only variable we have on the right hand side here is the x. Okay, the rho, the h and r are all constants except the x, which is a variable. So we can have something like this: half rho pi. You can have r to the power 4 over h to the power 4 multiplying. Okay, then from here you can bring the integral sign, and then you can have x to the power 4 dx, right? And then you're going to integrate this from 0 to h because you want the mass moment of inertia for the entire circular cone. So when you do this, you're going to have ix to be equal to half rho pi r to the power 4 over h to the power 4. Then you're going to have x to the power 5 over 5. Then have the limit here from 0 to h. So when you simplify this, you're going to have ix to be equal to 1 over 2 rho pi r to the power 4. And for the h, you can do some cancellation there. So all this will go, and then okay, let me write this. Okay, let's leave what I did earlier on. So we're going to have r to the power 4 over h to the power 4. Okay, and then now you're going to have times, we are going to substitute the boundaries or the limit into the expression. So you're going to have h to the power 5 over 5. Okay, so this was the reason why I was doing that cancellation. So from here, all this will go, and then this 5 2 will go. Okay, so let's simplify this and see. Okay, I have to free out some space before we continue. Okay, so now let's write down what you have. So now we have ix to be equal to 1 over 2 rho pi r to the power 4 h over 5. So this would be the mass moment of inertia of the entire circular cone. Okay, but we need to express it in terms of the mass m. Okay, So how are we going to do this? So for us to be able to express this in terms of the mass m, we have to divide it by the mass. Okay, so I'm going to have this divided by the mass, which is rho pi r squared h over 3. Okay, this is what we will have. Okay, so let's look at what will happen. So I'm going to have ix to be equal to 1 over 2 rho pi r to the power 4 h. Okay, so let me clean all this and then let me write it as 1 over 10. Okay, and then rho pi r to the power 4 h times, okay, times 3 over rho pi r squared h. Okay, so this is what you have now. So you can do some cancellation here. You can do some cancellation here. So this rho and pi cancel out this rho and pi, and then you have r squared here. So that means you're going to have r squared here also. Okay, and then the h2 cancel out. So let's write down what you have now. So you're going to have this to be equal to 3 over 10, 3 over 10, and then we have r squared left. Okay, so what this means is that we were having the actual mass moment of inertia, okay, and then we divided it by the mass, and then that gives us what you have here. Okay, so that means that for us to get the moment of inertia, we will have to multiply by the mass again so that we can get the actual moment of inertia. So we're going to have m here. Okay, so what is actually happening is that I cancelled, I divided by the m, and then I cancelled out the terms. Okay, that means that if I multiply it by m again, then I'll get the actual expression. So that's what happened here. So you see that for this m that I have here, okay, we have it to be equal to this. Okay, so if we multiply this expression by, if you have 3 over 10 r squared, and then you multiply it by this expression that I have here, you're going to get the mass moment of inertia that we got at first before we were asked to express it in terms of the mass m. Okay, so that's what happened there. If you want an actual example of what I did, um, I will show you. Okay, let me explain better what happened there. Okay, so let's see what happened. Okay, so let's see that we have the mass moment of inertia to be ix to be equal to 6. Okay, and then we have the mass m to be equal to 3. Okay, and then I want to express this mass moment of inertia in terms of the mass m. Okay, what I'll do is that I will actually divide it by the mass m. Okay, I can divide it by the mass m, right, which is 3. And then when I do this, I'm going to get what? The answer to be 2. All this means is that if I multiply 2 by m, that will still give me 6, which is the mass moment of inertia. So the same thing that I did here, I was having the mass moment of inertia, but we were asked to express it in terms of the mass. So I divided it by the actual expression we got for the mass, and then after that I was able to bring the m. Then I then got our mass moment of inertia in terms of the mass to be 3 over 10 multiplying m r squared. That's all for this video. Thank you very much for watching. Please make sure you subscribe to this channel.